Hello and welcome to my SAS and SAS minor presentation. So first, let's take a look at our data set. In here, what we have used to analyze today is a heart data set where our target variable is whether a person has a heart disease or not, where these were coded as 0 as doesn't have a disease and 1 is the person does have heart disease. These are all related variables with that target variable where Ca is the number of major vessels in heart, col is cholesterol level, Cp is chest pain, and all these variables were coded as the type of variables they are. And they are so moving on from there. Let's take a look at the EDA of the data. Here we can see that in the static explorer will show some information whether the variables are related with its target variable. We can see in the chi-square table that these variables have like a chi-square value statistic with whether these are related with our target variable. Moving on from there, the next job is to partition the data. The data partition involves training 60%, validation 20%, and test 20%, so that we use majority of the data in training and less in validation and less in test. So moving on from there, I have included a control point node here so that we can fit multiple models, and later at some point we can so that we can compare those. So for the neural net model, we have used one layer architecture, and which means that the data transformation from input to output has only one layer within them with three hidden neurons. If we take a look at the neural net output, we can see that our target here, the target variable has only one output node since we have only two classes, and our response is whether a person has a heart disease or not. So first, let's take a look at the fit statistic here. In the misclassification table, we can see that our training error rate is 13%, and in the test also 13%, which shows that our model is not overfitted since our training and test they have same error rate. This is my first concept that I've learned from the class that if the test error rate is far worse than trained, then the model is subject to overfitted. Also, another concept that I would like to illustrate is the true data generating process. Since I don't have any domain expert in this area, whether it is possible to predict heart disease with those variables present. So I cannot conclude that the model is actually doing a good job, although at face value it looks that the model is have done a really good job. So from there, we can also take a look at the classification table that we have, and here we can see that we have this false negative, true negative, false positive, and true positive, and also we can see the percentage of the validation set and also the training set. There and also in the validation set we can see that there is no false negative, but there are some false positive here. So we can say that since the specificity of our model is actually is actually quite good. Moving from the neural net output, let's take a look at the naive-Bayes model. In the naive-Bayes model, I have used this naive-Bayes model in here, as an option. And if we take a look at the naive-Bayes output here, in the fit statistic, we can take a look at the misclassification error rate. And in the training, it's 16%, but in the test, it is far more smaller. So we can also conclude that the model is not subject to overfit. Maybe there might be some maybe there might be a hint of underfitting there since the training error rate is higher, although in the test rate is smaller. This can also happen since our data set, as in the testing data set, the data set is only 20%. That might also be the reason. And point to be noted that this data set only have 300 observations, so the data is not that large. So moving on from there, let's take a look at the comparison of the model. In the model comparison node, we can take a look at here. We can see that the classification error rate between these two models. The classification error rate between these two models is in neural net is 13%, in naive-based classifier it's 11%. So basically we can say that maybe naive-based classifier has performed really well. My third concept in here that I've learned from the class is the cumulative lift curve of these both models. We can see that as the depth has risen, and these both of these models have merged together at the same point, and we can conclude from here that at this depth and at this depth, the neural net performs much less compared to the naive base. But as the data has performed and as the depth of the data has risen, the neural net has far more better lift than compared to the naive base classifier. So this is my third concept that I've learned from the class. And in terms of comparison of both of these models, the naive base classifier has done the better job. Thank you.